the problem says a box contains 12 light bulbs, of which 15 are defective. All bulbs look alike. A sample of 3 bulbs are chosen. Now, if they choose 1 bulb, then you don't need counting technique, but 3 bulbs are chosen. So to handle that, we need to use counting technique. First, you need to figure out exactly how many good bulbs, how many bad bulbs are there. 12 light bulbs include 5 defective. So that means 12 minus 5, 7 are the good ones. So I'm writing down clearly how many good ones are there and how many bad ones are there. Those numbers have to be first worked out. Very often students use the wrong numbers. So 7 good and 5 bad. I'll call them bad, good and bad. Okay. We are taking 3 bulbs, and first question is, what is the count of the sample space? The sample space, the count of the sample space is same as number of ways of selecting 3 bulbs from the 12. So sample space will have all the possible ways of selecting 3 bulbs from all 12 bulbs. Some of them will be good, bad. We don't care for the sample space. So therefore, sample space count equal to combination 12 comma 3. So that'll be factorial 12 over factorial 9 times factorial 3 equal to 12 times 11 times 10 over 3 times 2. 3 times 2 is 6, divides 12 into 2. So I have 220. Now the event that we need to do in part B is what is the probability that all 3 are defective? So all 3 are defective means this event is going to have, if I call all the bad ones as B1, B2, B3, all the way to B5, then all the elements that will make this event happen, all the elements in the sample space that will make this event happen will be the ones that have like B1, B3, B5, or B2, B1, B5, things like that. So these elements are in the sample space, but these are the ones that will make the event of having all 3 defective happen. So how do I count this? Anybody? What is, it's clearly a combination of what numbers?
5, 3.
Right, all 3 have to come from the 5 bad ones. So 5, 3. And that's factorial 5 over 2 times 3. And that's 5 times 4 over 2 equal to 10. So the probability for that event is 10 over 220 equal to 1 over 22. Part C says, what is the probability that exactly 2 are defective? So this event, if I call it F, it'll have to have something like B1, B2, and G1, 2 defective. B3, G2, B4, stuff like that. So 2 of them have to come from the good, and 2 of them have to come from the bad one, and 1 has to come from the good one. So the count of that event is a combination of 2 bad ones have to come from the 5 bad ones, so 5 comma 2. And then number of ways of getting good one is, anybody?
Times combination of 7, 1.
7 comma 1. There are 7 good ones. 1 of them has to come out of that. And because of the multiplication principle we learned, the product will give you the total number of ways of having that. And C52 is same as C53, that will be 10. C71 is 7, so that's 70. So the probability of F is 70 over 220 equal to 7 over 22. Part D says, what is the probability that at least 2 are defective? That means 2 or more defective. So 2 bad, we're selecting only 1. So 2 bad, 1 good, or three bad, all three bads, because it says at least two defective means two or more defective. So two bad and one good is one possibility, or three bad is the only other possibility, and that's it. So count of this event, if I call it G, count of G is count of getting two bad, one good. We already counted that. Two bad and one good. That was 70. And count of getting all three bad is also, we also counted that in the first part, and that was 10. So therefore, wherever OR is, you have a union. So we know that count of union, A union B, is equal to count of A plus count of B minus count of A intersection B. Now, clearly there's nothing common between these. These have two bad and one good. These have three bad, so there's nothing common. So therefore, they are mutually exclusive, and intersection is empty, count of intersection is 0. So therefore, it's count of A plus count of B, 70 plus 10, 80. And therefore, probability of G is 80 over 220, which is same as 8 over, you won't let me write there. So probability is 8 over 22, 80 over 220, which will reduce to 4 times 220, 4 over 11. That's the answer for that one. I can write below this level. Maybe I can. 8, yeah, 8 over, no, I'm sorry, 80 over 220 equal to 8 over 22. If I reduce by 10, I can reduce by 2 again, so 4 over 11. Okay, so that finishes that. Now this problem, like example 4, we did before, but I'm going to do that anyway. Clear this board. A fair coin is tossed 10 times. That means you could toss it once and observe what the outcome is, toss it again, observe what the outcome is, and all those outcomes together, 10 of those is your outcome. That's same as saying toss 10 coins and observe the heads and tails. So your sample space is going to have basically 10 of H's and T's. So H, T, H, 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 T, T. This is just one example. Okay, I have 3, 6, 7, so 8, 9, 10. This is just one example. All bunches of H's and T's, but total count has to be 10. So this is what we're going to have. So count, how do I count the number of elements in here? We did this before, so hopefully you remember. Anybody? What method should I use? Let me put it that way. The elements in the sample space are basically code words made with H and T only, 2 letters, H and T only, but they're repeated. Repetition is allowed.
Permutation?
Is that permutation? No, we are not. See, when you allow repetition, it's not permutation. Remember, permutation is count without repetitions. So it's not permutation, and it's not combination either.
Is it the box method?
Box method?
Right. Box method is the only way when you allow repetition. So 10 boxes to fill, right? 10 of those H's and T's will be there. And how many ways are there to fill each one?
10 ways?
No, each one doesn't.
2 ways.
2 ways. Only HOT will go in each box. So 2 ways to do each box, HOT. So product of that will be 2 to the 10. That's our count of sample space. 2 to the 10 is, let me quickly compute that, 2 to the 2, 4. Okay, 256 times 4. Okay, so that's the count of the sample space. Now let's go to the question. What is the probability of obtaining exactly 5 heads? So our event is going to have exactly 5 heads. So let me write down a couple of samples of elements in the event. H, T, H, H, T, H. You had to have exactly 5 heads. So 5 heads. Okay, this is one example. There are 5 heads, but the heads can be anywhere in the list. So there are many more. How do I count that? Remember, this is not new. We did this before. Count of event E. Anybody? Okay, this is same as asking the question this way. I need to have I have 10 boxes and I need to have exactly 5 H's. So if I can place the H's here, one here, one here, one here, here, and here, that's one way. Similarly, if I just, I can choose another 5 boxes for placing that. So they're placing the H.
Is it combination 10 comma 5?
Right. Number of ways of choosing 5 boxes from 10 boxes. We did this kind of problem with the zeros and ones, and then also with H's and T's with different number of boxes before. But we did the same thing before. So C10 10 5 is the answer to that, because that's same as saying the number of ways of placing H's here is same as number of ways of choosing 5 out of 10. The remaining 5 will be T's. Okay, so this will simplify, C10 5 will simplify to 10 factorial over 5 factorial times 5 factorial, which will be 10 times 9, 8, 7, 6 over 5, 4, 3, 2. 3 times 2 cancels with the 6. 5 reduces the 10 into 2. 4 reduces 8 into 2. So we have 2 times 2, 4 times 9 times 7 to multiply. So 4 times 9 times 7 is 252. So therefore, the probability of E is 252 over 1024. We had to reduce that, but I'll leave it at that and go on to part B. Part B says, what is the probability of obtaining between 4 and 6 heads, which means 4 heads or 5 heads or 6 heads. So this event G represents getting 4 heads or 5 heads or, what's 4 and 6, yeah, 6 heads. So I'll just do the counting of that. Getting 4 heads would be same as choosing 4 boxes from 10 boxes. So C 10, 4. And wherever OR is, it will be plus, because that's union. And as I explained, count of union would be same as count of sum of the count of each set, each event. So number of 5, we just did that, C10 5 plus C10 6. And then you had to simplify that and divide by the 1024 to get the probability. All right, moving on. Exercise 2, that's exercise for you.
Question, sir.
Sure.
Remember when we did combinations before, we had to multiply them?
Multiply, yeah, that's, yes. So you're wondering when it is multiplication?
How would we know when to do multiplication or addition
Okay, here,
between the combinations?
yeah, here the word is or, right? So wherever or is, it's union, right? You remember that. Because A union B is what A union, so let me erase part of this. Okay, you know that X belongs to A or X belongs to B is same as A union B, right? If anything that belongs to A union B would be either belong to A or belong to B. So that's why if I say 4 heads, that means I'm talking about the set that contains all the elements of the sample space with exactly 4 heads. This is a set. And this is a set that has elements of the sample space that have exactly 5 heads. This has elements of the sample space that have exactly 6 heads. So when I say the element should be either here or here, that's same as belonging to the union, right? That's how we understood the union. So the union of those 3 events, this event getting 4 heads and 5 heads and 6 heads, those 3 events, you need to take union of. And then we know that the count of A union B, union C, we wrote it for 2 sets, but it's true for any number of sets. A union B, union C is count of A plus count of B minus count of C minus count of the intersections. The intersections are empty because this event has all of them with the 4 heads. This event has all of them with 5 heads. So there's nothing common. So in these problems, always intersections are empty. So therefore, count of union equal to count of, the counts will be added up. Now the product came up in the problem where it said there are 5, I think it's, I can go back to that problem. 12 light bulbs with 5 defective. And the question was exactly 2 defective, part C. So part C says, what is the probability of exactly 2 defective? So you have already chosen 5 defective bulbs. And so you need to count how many of those elements in the sample space have exactly 2 defective. That means 2 have to be defective, 3 have to be good. So so that would be, I'm trying to write down some samples. That will be 2 bad and 3 good. So B1, G1, B2. We're not arranging in any order, so just collecting. So that's why I'm writing them in random order. And 3 bad ones have to be there, and the others have to be good ones. We're selecting how many? Oh, we're only selecting 3, sorry. So 2 bad ones have to be there. All right, so this is one example. And the other one is G1, B2, B3. So we need to count how many of these things are there. Okay, so counting how many ways are there to select 2 bad ones. Okay, and that will be I'm trying to explain why we had to multiply, right? The number of ways of selecting two bad ones is count of getting two bad ones is C 5. No bad ones. How many bad ones are there? 5. So 5 comma 2. And number of ways of getting one good is C 7 1. Now, why do we need to multiply? Because let's collect the all of them with the two bad ones. Two bad ones. Let me write some of them. B1, B2, B3, B4, B1, B3. These are some of the ones with the two bad, right? And then the one good can be, that's another event. So that event has G1 or G2 or G3 or G4. And the count of that is what C71 is, which is equal to 7. And this is 10. So there are 10 of those, 7 of these. And why multiply? Because now look at these events, elements in the first set, elements in the second set. If I take B1, B2 here and combine with G1, that's one element. B1, B2, and G1, right? One element in the event that we are looking for, the event up here, this event. We're trying to count how many are there. So if I take same B1, B2 and combine with the G2, that's another, right? Okay, so every element in the first set can be combined with one element here to get a whole bunch of them. And if I combine all of them with the second one, that's another bunch of them. So that's why the product gives you the count, because it is similar to the same question we discussed before, the number of ways of going from Chicago to or New York to Chicago 2 ways, and number of ways of doing the second part, going to San Francisco 3 ways. Then the total number of ways is combining each one here with each one will give you one set of ways, and then the second one combined with each one there will be another set. That's when it's multiplication, 2 times 3. That's what the multiplication principle is. That's exactly what's going on here. Each element in this first collection can be combined with each element in the second collection to get the element that we want, right? And there are, the number of ways will be the 10 times 7, right? Because of this multiplication principle. You understand the difference now?
Yes.
Okay. Because the two bad ones and the one good are being combined to get the elements of the of the event. So when you do combine them to get the elements, the multiplication principle applies. But in the other case, it's or. Or means union, and that's when the counts will be added up. Okay, I have a mess on this on the board. Let me clear that. So we finished that, and I'm going into the exercise 2. One family is randomly selected from those families that have 2 children. What is the probability that the family has 1 boy and 1 girl? So let me see if anybody can do that. So the families we are looking at, all of them have 2 children. And if I select one family randomly, what is the probability that they have 1 boy and 1 girl? All right, can somebody tell me what the sample space would be?
4?
4 elements in the sample space? Is that what you mean?
Yes.
Okay, can you tell me what they are? If it's 4, then we should be able to write them, right?
Yeah, it could be 1 boy, 2 boy, then 1 girl and 2 girl.
Or in other words, boy and girl, or boy first, girl second. The order matters, right? Because, you know, first child is oldest child. So boy first, girl second, or girl first, boy second. And what are the other ones? Boy, boy, and girl, girl, right? Is that what you meant?
Yes.
Yes. Okay. And so the event that we need the probability of would be what? That'll be GB and BG, isn't it? Right? 1 girl and 1 boy. So therefore, the probability of E is 2 over 4, which is half. Right, very good.
Oh, Professor, my exercise is different from the one in your worksheet.
Oh,
That's why I was confused.
you must have, I didn't change this recently. This was done some time ago. So you must have printed it before that.
No, I printed it out today, actually.
Today?
No, I'm sorry. No, I printed it up before the last class.
For the last class.
Yeah. For me, I have 2 boys and 2 girls.
Uh-huh.
That's why I was confused.
That's what I have as example 5.
Oh, yeah, I don't have example 2 then.
Oh,
I
you
have
don't
exercise 3.
okay. All right, you don't have exercise 2, so you must have printed it before I made that change. So sorry.
Okay, I'm sorry.
Yeah, sorry about that. But wait until the class, because you know, before printing it, you may want to wait close to the time we discuss the worksheet, because I do change, but I don't change at the last minute. I make the change much earlier than the class in which we discuss that. So I don't believe there's any other change. I just wanted to make ask that question before doing the example 5. So it's, you know, you can handwrite that problem in your printout, then you will be set. Example 5 says one family is randomly selected from those families who have 4 children, and what is the probability that the family has 2 boys and 2 girls? So I wanted to do that exercise so that you get the idea first, and now when you go into 4 families, I mean 4 children, it becomes a little more complicated. Now you may have to use counting technique. So let's go back to this previous problem before the example. And can you see that the count of the sample space can be done as, if you look at the elements in the sample space, they are basically code words made with 2 letters B and G with repetition allowed, right? So to count them, I could have done this. I could have said 2 boxes to fill with B and G, 2 ways to fill the first one, 2 ways to fill the second one. And that's why we have 4 elements in that sample space. So look at this example 5. And can you tell me how many elements are in the sample space?
2 over 4.
The
16.
number of elements in the sample space.
16.
Okay, right, 16, because there are 4 boxes to fill with B's and G's, right? So 2 ways to do each one, and so 16 ways. So that's how many elements are in the sample space. See, when you're doing only 2 children, you can do manually without having to use counting methods. But when you go into 4 children, you had to use counting method, because you cannot write down all 16 of them. It'll be just too much effort. Now the question is, the family has to have 2 boys and 2 girls. So how do I count the number of elements in that event?
Combination of 4, comma 2 or not?
Right, combination 4 comma 2, very good. Because that's exactly same as asking in these 4 boxes, in how many ways can I place 2 B's? The other ones will be G's. So B and B here will be 1, B and B here and B here will be another. But the simple way to count that is number combination of, or number of ways of selecting 2 boxes from the 4, which is same as C42. And that's equal to factorial 4 over 2 times 2. So 4 times 3 over 2, 6. So therefore, the probability for that is 6 over 16. So as you can see, counting technique is necessary when you go into a higher number of children. So this method can be used even if the number of children are 5 or 6. This method will apply. Okay, so now one of the most important applications of probability is lottery. We can calculate the chances of winning. And if you calculate the chances of winning, you will not play the lottery. It's that bad. So let's clear the board and do this problem. SAT state lottery requires you to select a sequence of 4 different numbers from 0 to 39. Now, notice that it says 4 different numbers. That means no repetition. They're going to be 0 to 39. This is how the lottery is, but you know, the lottery I'm talking about here is reduced, a smaller one. The actual lottery allows you to select 6 numbers in certain range. And then only if all 6 of them match, not only match the numbers they find, they come up with in their in the actual drawing. That not only they have to match the numbers, they have to be in the right order, same order. Only then you'll win. So here's how they do it. You know, to come up with this the drawing, they put all of them in a container. A huge container will have all these balls with numbers written on them. 19, 8, 25, 39. All these numbers will be written on them. And then they shake it up to make it completely random. They shake this up and then they have an opening where one of them can come out. So they shake it up and then allow one to come out, and that one comes out first, and that is one of your number. So let's say that's 15. And then they continue to shake it up, and then this will be closed, and then shake it up, and then they open it so that another one will come out, and there's another one. So they keep doing that 6 times. Now we're doing 4 times. So these numbers are the results of the drawing. So let's say these numbers are 11 and 25 and 36 and 9. Then you had to get these numbers and you had to get them in that same order to win. Okay, so that's how it's done. So let's calculate the probability. Now, for our purpose, the numbers are 0 to 39. Okay, then how many numbers are there? How many numbers are there to choose from?
39?
No, 0 included, so 40.
40.
Okay, so from 40 numbers, 4 numbers are going to be selected, and the order matters, right? So, because you had to get them in the exact order to be able to win. So rearrangements will be different elements of the sample space, right? You select 4 and rearrange. All rearrangements are going to be different elements in the sample space. So the count of the sample space is, what would that be?
40, comma 4.
Permutation or combination?
Permutation.
Permutation of 40, 4. You're right. Very good. from 40 numbers, all the different ways of selecting 4. These will be in the sample space. So let's simplify that. Factorial 40 over 40 minus 4, 36 times 4 factorial equal to 40 times 39 times 38 times 37. So we stop at 37. And then 4 factorial will be 4 times 3 times 2. I can reduce that to a number. But my question is, out of all these elements, how many will make you winner? In other words, how many elements are in the event of winning?
4,
Why 4?
because there's going to be 4 numbers selected out of the 40.
I just explained to you in this example up here that if the winning number from the drawing would be 11, 25, 36, and 9, then you had to have exactly those numbers in that order to win, right? So
For our question, it says, but in the wrong order.
the wrong order means you don't win. It has to be in that, all the outcome, the number you chose, all those numbers you chose have to be there in this list, and they have to be in this order. You must have, when you play this, you actually fill out a form, you write down exactly what numbers you chose. And those numbers have to match exactly this. Only if it is 11, 25, 36, and 9 in that order, then you win. So how many elements in the sample space will make you
Professor,
win?
I have a question.
Yeah.
Isn't that the combination formula? Like the permutation formula would be 40 factorial over 36 factorial.
Oh, okay. Yes, I used the combination formula. You're right. Yeah, the 4 factorial should not be there. You're right. Everybody understood that? It's a permutation. I need to use permutation formula. I was using combination formula. Thank you for bringing that up. So it's 40 factorial over 36 factorial. That's a permutation formula. So this product is your number. Thank you for that. So still my question is, how many elements in this sample space will make you a winner?
Is it just one?
One element, exactly. Because sample space has so many elements. Actually, if you simplify this, it is actually equal to 219. I already have that on the board. 219, 3360. That's 2,193,360. That's what that number is. So those are all rearrangements of 4 numbers selected from the 40 numbers, 0 to 39. Out of all those, only one will match exactly the winning number. Only one of them is going to match the winning number, because it has to be the winning number, the 4 winning numbers in that order. So there's only one. So the probability for winning is 1 over 2,193,360. So you can see it's so small number, right? This is working with 4 numbers. So the actual lottery is with 6 numbers. So that's even smaller. So even if this lottery is going to use 4 numbers, what does this mean? Let's say when you win, you may win $1 million. But if you're paying $1 to play the game, this probability means you must spend $2 million to have a chance of winning. To have a chance of winning once, which means to get that 1 million, you have to spend 2 million to begin with. So that's why the probability is so small to win. Let's go to the second question in this problem. It says, you will be a booby prize winner if your selection is correct, but not in the right order. So basically, you will be a booby prize winner if you have the same numbers, the winning numbers, but not in the right order, like this, 11, 25, 36, 9. If they're the winning number, and if your number is 25, 9, 36, and 11, you will win. Or if you have 9, 11, 36, 25, then you will win the booby prize winner. So basically, your chance is getting a little more, but how do we calculate this? So the event of winning booby prize has how many elements? Can somebody tell me how to count that?
Is it permutation of 4, 4?
Right, exactly. Excellent. I'm glad to see one student figured it out. It's basically all the rearrangements of these 4 winning numbers. All the rearrangements will be number of ways of getting all 4 of them rearranged is same as P4, 4. That's how many. In other words, if you rearrange these 4 winning numbers, and if any one of them is the actual outcome, actual number you have, then you win booby prize. So therefore, the number of elements in the booby prize winning is P44, which is factorial 4, which is equal to 4 times 3, 12, 24. So the probability for winning booby prize is not 24 over the 2,193,000. Why? Because these 24 rearrangements of the 4 numbers includes the winning arrangement. The winning arrangement is one of them, isn't it? So that winning arrangement, if you get that, you will be first prize winner. So to be a booby prize winner, out of the 24, you had to get the other one of the other 23. One of them is the first prize winner. So there are 23 elements in the booby prize winning, not 24 really, because 24 elements are there, but one of them will be the same as first prize winner. So 23 of them will make you booby prize winner. So this is the answer for that. 23 over that.
Don't we just subtract, right?
Subtract what?
Aren't we just subtracting then from the probability of E and the probability of F?
Uh, um, um, essentially, yes. In other words, there are 24 arrangements of the 4 numbers, and out of those 24, one of them will make you first prize winner, and that's why you have this probability for the first prize, and 23 of those will make you booby prize winner. So yes, they both add up to 24 over 2,193,360. But when you are doing this problem, you know, you cannot look at that way. You have to figure it out this way. You have to calculate all the different ways of rearranging the numbers, and then there are 24 of them, so 23 of them will make you booby prize winner. That's how you have to look at it to do the problem. All right, so that finishes our chapter on probability. This is one chapter of probability. And I didn't divide the probability into chapters, but this is where one chapter of probability finishes. The other chapter begins at conditional probability. That is going to lead us to many other concepts. And so the whole thing will go into another chapter of the book. So let's start doing conditional probability. Now, this concept you have to understand, and if you don't understand this, you will be lost for the rest of the probability theory, and you'll be also lost for the statistics. Well, the statistics we're going to be doing doesn't use much probability, but when you go into the statistics class, some of you are going to be taking statistics next semester. So when you go into that statistics class, you're going to use a lot of probability theory. So in this course, you can still handle the statistics that we're going to do, even if you're lost in the probability. But when you go to the statistics class, you won't be able to handle it. But so let me, I have good examples carefully chosen so that you will understand the conditional probability. So let's get started. The probability that an event F occurs, given that another event E has occurred, is called conditional probability. See, sometimes one event occurring will depend on whether another event has occurred or not. So that's when we have conditional probability situation. My examples will make it clear, but a conditional probability means a probability of an event occurring given another event has occurred. So we write that in this, using this symbol, probability of F given E. That's how we read it, but it's written as probability of F and the vertical line symbol E behind it. So it means probability of F. It is probability of F given E has occurred. The one in the back, the second one is the one that has already occurred. So this means the second event is going to affect the event E is going to affect F, and that's why we write the probability this way. Probability of F given E has occurred. Now this example should make it clear. I chose the example very carefully. I'm drawing a card from the 52 card deck. So this card, one card I'm drawing can be anything, any one of the 52 cards. And then it says, find the probability that it is a king, given that it's face card. So in other words, they have taken the card out, but they are telling you that it's a face card. Then what is the probability it's a king? Now, king is a face card, but there are other face cards. So how many face cards are there? The king, queen, four kings, four queens, and
4 juniors.
I'm sorry? For Jack.
4 juniors.
Jack, you mean. Four kings and four queens and four jacks. Ace is not considered to be a picture card. That's 12. So the question is, so if I tell you I took the card and then I'm telling you it's a face card, so what is the probability that it's a king? So that means if the event that has happened is it's a face card. So we can write this in the following manner. The event E is defined as card is king.
Would it be 12?
12 face cards are there, yes.
Okay.
But I'm going to get to the probability. So let me define the event E as card is a king, and define the event F as card is a face card. Then how do we identify this question? The question is find the probability that the card is king, given that it's a face card. How do I identify that as a conditional probability? It's probability of what given what?
Would E be probability 52, 4?
No. Don't get to the probability yet. I'll explain that in a minute. Right now, my question is, how do I write this question as a conditional probability question using P of what given what? That's my question. E is defined as card is king. F is defined as card is face card. Then the event of this question, find the probability that the card is king given that it is face card, can be written as what? P of what slash what?
E/F.
Right, E slash F. It's not really slash, it's the vertical line symbol. On the keyboard, it is shift slash. It's E given F. We just read it as E given F. That's what we do. So that's what we are looking to find. Probability of being king, card being king, given that this event has happened, which is card is a face card. So if you know that card is face card, then what is the probability that it is king is the question. Now, here is how we find the probability. The card is already known to be a face card. That means our sample space doesn't have 52 elements anymore. The sample space now has how many? 12 elements, right? Because we already know it's a face card. So what is the probability then? What number divided by what number?
4/12.
4/12 is right. Very good. So because now we know the card is face card, that means our sample space comes down to all the face cards, which is 12. It has 12 elements. Out of the 12, 4 kings are there. So probability for the card to be king given face card is 4/12. That's all it is. The sample space is going to change. Sample space basically becomes the event that has already happened, so you need to use that count. So that's how you do it. Let's go to the exercise 3. A card is randomly taken from a deck. What is the probability that it is a jack? Now, the first question is just probability for it to be jack, okay? That's not conditional probability. Okay, so what is that?
4/52.
4/52, right? Because sample space has 52 elements and 4 of them are jack. Part B says, what is the probability that it is jack if it is already a diamond? I have
Excuse
taken,
me, Professor.
yeah,
How do you read 2/52?
because a card is randomly selected, what is the probability that it is a jack? Oh, it's not 2, it's 4.
Oh, yeah. Okay.
4 jacks, right? I don't know why I typed 2. I think the student said 4/52. I mistyped it. Anyway, there are 4 jacks, and out of 52 cards, so sample space has 52 elements, and so event has 4 elements because there are 4 jacks. Now going to the second part, part B, it says if it is already given, if you already know that it's a diamond, then what is the probability it's jack? Anybody?
4 out of 13.
4 right, 4, it's not 4/13. No,
1/13.
1/13. Because if it is already diamond, there's only 1 jack within diamond, right? Okay, everybody understand that? So if it is already diamond, then our sample space comes down to having 13 elements. Out of those 13, there's only 1 jack. So 1/13. Ask me a question if you're not following me. It's important that you understand the conditional probability. All right, if you understood that, then you should be able to do this exercise. A jar consists of 4 red marbles, 5 green marbles, and 3 white marbles. 1 marble is taken. And if I call the event E as marble is red, F is marble is not green, Then first question is, what is the probability of E? There's no conditional probability here, simply probability of E is all we need.
4/12.
4/12. So 4 marbles out of total 12 marbles. 4 red marbles out of 12. So 4/12 is right. Now, if anybody is not following anything, feel free to interrupt. Second question is, what is the probability of F? F is, the event F is marble is not green. Okay,
7/12.
7/12. Right, there are 7 green, 5, yeah, right. 4 red and 3 white have to be the outcome. One of the 4 red or 3 whites. So 7 elements are there that are not green. So therefore 7/12 is right. Very good. Now it says, what is the probability of E given F? Probability of E given F has occurred. So now it's conditional probability. E given F. That means I have taken the marble and I already know it is not green. Isn't that what it means? I already know it's not green. Then what is the probability that it is red? Event E is red.
4/7.
4/7. Right, exactly. It's 4/7. Because it is already not green means we are limited to 7 marbles now. The 7 marbles that are not green. And out of those, 4 are red. So therefore 4 out of 7. That is the conditional probability. Feel free to ask the question if you're not following any part of it. All right, the last question is find probability of F given E. F given E means E has already occurred. That means marble is red. What is the probability of F occurring?
7/12.
Not really. Keep trying.
Would it be 3/12?
No, you have to think a little bit further from the numbers. E has already occurred. What's the meaning of that?
Marble is red.
Marble is right. So it's already not green, right?
Yes.
That means it has occurred already. F has already occurred. If E has occurred, F has occurred. So the probability is 1.
4/12.
No, probability is 1. It has occurred already. E has occurred means marble is red. That means it is not green already. So
Is it because it would be 7/7?
yeah, you can put it that way. If not really 7/7, marble is already red. So there are 4 elements in the sample space, right? And how many of those 4 elements will make the event of not green happen? All 4 of them. If the marble is red, then it's already not green, right? So if you want to look at it that way, the marble is red means there are 4 marbles in the sample space. How many of those 4 will make the event F happen? All 4 of them, any one of the 4. Because if it is red means it's not green already, right? So you can think of it as 4/4, but another way to see that is if it is red, then if it is already not green, so therefore if E has occurred, F has occurred. And therefore probability of F occurring given E occurred is 1. Everybody understand it, or do I need to explain further? E has occurred means the marble is red. And that means your sample space has 4 red marbles now. Out of those 4 red marbles, which one makes event F happen? Any one of the 4 red marble will make the event F happen, because if it is red, then it's not green already. So therefore, 4/4. That's one way to look at it. Another way to look at it is if the marble is already red, then it is not green already. So if the event E has occurred, F has occurred too. So that's why the probability is 1. All right, let's go to example 8. A couple is randomly selected from those who have 2 children. What is the probability that they have 2 girls? We did this earlier, right? They're selected from those who have 2 children. So the sample space has 4 elements, right? BB, GG, and BG, GB. Remember, we wrote that. So 4 elements. Out of those, how many elements have 2 girls?
1.
1.
1.
So the probability is 1/4, isn't it? For the first part. The second part is, what is the probability they have 2 girls if you already know that they have at least 1 girl? All right, then if you already know that they have at least 1 girl, then our sample space becomes GB, BG, right? Boy and girl, girl, boy, boy, girl, or what else is possible?
2 girls.
2 girls. So these are the elements we are limited to. So what is the answer to the probability?
1/3.
1/3. So that's what you do. First, if the event has happened, then you can limit your sample space and then figure out how many elements in this sample space will make the event happen. There's only one element here that will make the conditional event happen. So 1/3 is the conditional probability. Okay, so that's what it is. Now, if you understood that, then you're good. Let's go to the Venn diagram and learn how to figure out these probabilities from the Venn diagram. So in this problem, Venn diagram shows you the count. The Venn diagram sometimes gives you the count of elements. Sometimes it gives you the probability for each section. Either way, we can work with it. So a card is randomly selected. What is the probability that it is Jack if it is already diamond? And what is the probability it's not Jack if it is already diamond? Those are the 2 questions we want to answer. To answer, we'll first define the event J as card is Jack. Define the other event D as card is diamond. Then the first question translates to probability of getting Jack given its diamond. So J given D is the question. And second question is the probability that it is not Jack, same as J complement. So complement of J given D, that's the second question. So if you're using we can do this directly without having to use the Venn diagram, but I wanted to show you how you can put these numbers in the Venn diagram. The elements in the events, I'm drawing on the board now. The sample space, we are drawing only 1 card, and so the sample space has 52. And the event of Jack has 13 elements. I'm sorry, not 13, 4. And event of diamond has 13 elements. Okay, and how many elements are common?
1.
1. There's 1 element in the intersection, the Jack of diamond. So there are 3 outside of it in here, 3, and 12 in here. Now, the probability that J given D means diamond has already occurred. So the part A, probability of J given D means diamond has already occurred means your outcome is in this circle. If the outcome is in this circle, then how many of those, so that means you are limited to these 13. Out of those, how many will make the event J happen?
1.
Wow. So basically, if you look at the Venn diagram, the 13 is the count of the diamonds, and only within the diamond, there's only one jack. So that'll be same as intersection. The intersection refers to the jack within the diamond, and that one, this 1 over 13. So this 1 divided by 1 plus 12, 13. That's your probability for the conditional probability. So if D has already occurred, you're limited to the 13 diamonds, and among them, there's this number of jacks are there. So that number over 13. Now look at part B, probability of jack complement given D. If D has occurred, how many are not jack?
12.
12. Any one of these 12. So to do the jack complement, you actually look at the complement of jack within the diamond. Within the diamond, the complement has 12. So that 12 over 13 is your answer for that. So if diamond has already occurred, so your denominator is going to be a number of diamonds. And within the diamonds, there's only one jack, so the numerator is 1. And if diamond has already occurred, denominator is 13. How many of those diamonds are not jack? 12. So 12 over 13. You can look at it, you can do it both ways. The reason why I wanted to introduce the Venn diagram is because when we get to the harder problems, Venn diagram will become useful to find the conditional probability. Okay, so let's do the example 9. This gives you numbers instead of probabilities, but we can still work out everything with the numbers. So E has, English has 40, English, 40 elements, 40 students are taking English, and 50 are taking math, and 12 are taking both, so 12 goes in the intersection. Now we can figure out the remaining sections. 40 minus 12, 28, 50 minus 12, 38. So what is the probability that student is taking English? Oh, that'll be 40 over 200, right? Part A is direct question, 40 over 200. That's not conditional probability. Part B is the student is from those who are taking math. We are randomly selecting a student and we know that he's taking math. Then what is the probability he is taking English? What are the numbers?
12
out
over
of
50.
12 over 50 is correct. That's right. Excellent. Because we already know the student is taking math means you're now limited to the 50 students here. Out of those 50, how many are taking English? 12. So 12 over 50. That's exactly the answer. Okay, very good. Sounds like you understand it. And so you are ready to do your problem. So yeah, quickly, let me ask you this question also, part C, and then we'll be done. Part C is the student be selected randomly is already known to be taking English. Then what is the probability that he is taking math?
12 over 40.
12 over 40, that's right, 12 over 40. Because now we know that the student is taking English means you're not now limited to this, English. Within that, how many are taking math? The 12. So the numerator numbers is always intersection. And the denominator is whichever event that has happened. Okay, so we will leave it at that and continue in the next class. So you have the assignment already, and it's due Wednesday. Our test is tentatively scheduled to be 2 weeks from Wednesday, 2 weeks from coming Wednesday. We should have finished everything by then. It could be moved either way, forward or backward, but tentatively 2 weeks from Wednesday. And the practice test is, the written test is already there in your supplements. And you may want to print that and start working on them and bring up your questions. I will use one class to go over questions on the practice test. But if you start early, then you'll have plenty of time to finish it. So you may want to start early. All right. Enjoy the rest of the day. I will see you Wednesday. I have next office hours will be Tuesday. You have received my email that I have changed my office hours to be able to help you better. So next office hour is tomorrow at 5 p.m. All right. Have a nice day, everybody.
Thank you. You too, Professor.
Yep. Thank you. Bye.
You have a nice day.
Bye. Bye now.
Thank you so much.
Mm-hmm.